All right, so let's talk about the remainder of chapter 2 of volume 2. The rest of this lecture, I don't know, in a lot of ways it's kind of light. Some of the things we've talked about have been heady, especially chapter 16 conceptually was, The things we're going to talk about today, some of you probably already know because there's a lot of you going to be medical people. The math isn't hard, and as we go farther and farther into the lecture, it's going to be more and more just kind of get the concept and move on, okay? Everything we're going to talk about is about optical instruments. Sometimes this is a whole chapter unto itself, but we're going to take what we learned about lenses and mirrors and sort of look at some applications of those, and then we'll be done with chapter 2. And yay, that'll be over with. We can move on to chapter 3 while you're studying for an exam next week, which sounds fantastic, right? So, first thing we need to discuss is the human eye. Any eye experts in here? Anyone going to be an ophthalmologist? No? Anyone know anything about the eye? Why are you all so quiet? Is it because it's Friday or because of those two people back there? Yeah, just be yourself. I'll try to be myself, but I'm not going to pull it off terribly well. What's that? It looks like he's trying to record this. Are you recording? Just a little bit. Okay. Yeah, thanks. And then that'll get sent back home to my brother, and he'll be like, look at you. You look like an idiot. And then, yeah. So this is like Family Week. You all met my nephew on Wednesday, and I didn't know this was going to be Family Week, but alas, then you meet my parents today, so fantastic. All right, let's talk about the eye. We're actually going to do something today. So there on the left, a cross-section of the eye. We're not going to get into the details of all the parts. We just want to think about it in terms of an optical system. We look at objects that are some distance away, and there's a lens, right? So this is really no different than some of the situations we've been looking at, except now instead of a screen that's like a piece of paper or something like that we project the image on, we have the retina, which allows, there's an image that's formed there, and then the retina picks that up and turns it into electrical signals, which our brain somehow means this stuff that we see around us, all right? So you can see there on the right, if we're looking at something that's really far away, let's zoom in. Why not? Look at that beautiful eye. Where you're looking at the same sort of ray diagram we had before. We've got the P ray at the top, the midpoint ray at the bottom. They're just showing two of the rays, and you see that it gives us a smaller image than the object itself, and it's also inverted. What type of image is it? Real or virtual? It's real. Those are actual light rays that are coming to a focus at that point. That's a real image being formed on the retina. Thankfully, it's reduced in size, because how terrible would it be if all the images formed on the back of your eyeball were either larger or the same size as the object itself? It would be odd-looking creatures. We'd need much larger eyes with much bigger retinas, so it has to be somewhat reduced. Keep in mind that as the object is farther away, it's more relaxing for the eye. Notice it says there that you have relaxed ciliary muscles, which allows the lens itself to change shape and change its focal length, which is nice, right? Instead of having a fixed lens system where it's like you have one focal length, we can look at things at a variety of distances and still focus on them and not have any problems. As the object is farther away, those muscles are more relaxed, and it's just, I guess less painful to look at something. And maybe you've experienced this as something gets closer and closer and you still try to focus on it. I don't know, you're all terribly young, so maybe you can read things like right here and you don't feel anything at all. But maybe you've had the idea that as you try to look at and focus on those things that are really close to your eye, like you can sense kind of some tension next to your eyeball. As the things get closer, it has to curve the lens more to make a smaller focal length, and it's just more work for the eye all around. So if something's far away, this is good and happy, but if something is close, it becomes more difficult. Let me add to this that if it's, we'll say, very far away, you end up with roughly parallel rays. And this is a case where it's the easiest. The farther the object gets away, the more parallel the rays are. So ideally, with any lens correction that we do, if maybe your eye is not working properly, or if we build another instrument to look at things, creating images that I'm going to look at that don't appear really close to my eye is better for the eye. It's easier to look at something if it's farther away, and it's just less eye strain overall. So let's expand this in terms of the normal eye. And I hesitate to use the word normal because I don't know that any of us really have an eyeball that's anything like anybody else's. Maybe we should call this like the standard eye, the numbers we're going to use that sort of represent standard vision, even though most all of us diverge from that somewhat, especially right here at the start. The near point of the eye is the closest object distance, the closest the thing can be away, and you actually get the eye to form a clear image. Notice this is probably larger than what you're expecting. 25 centimeters is considered a normal near point of the eye. 25 centimeters is like, what is this, about 10? Does that look about right? I don't know. Help. Yeah, so 10, I'm moving things around as I do it. 10, 20, maybe like here. So just kind of normal arm's length. If you can see that, you're considered to have a normal near point. But I'm guessing there's probably a lot of you that like lie in bed at night with your phone, right? And then like it's like on the pillow with you, and you're kind of like doing this number. That's, and you lay there for hours and just look at your phone, maybe watch a movie, and you're like, my near point is 6 centimeters. Like, this is fantastic. I hate to admit this, especially in front of my parents, but I noticed about 2 years ago, I had like that first inkling of, like, I was looking at something right here, and I was like, my eyes hurt just a little bit, and things aren't quite in focus, and I just had to go. And then I just felt sadness pour through me, because I knew this is the time where my near point is getting farther away as I get older, and then you have this situation, right? And then the reading glasses, and you can't hold things far enough away, and alas, the near point is breaking down just a little bit, just because the eyes are being strained. So 25 centimeters, like maybe now yours is at 6, but it's going to move back to 25, and it's going to go farther than that given enough time. So we can represent this with a symbol. We're just going to call this D sub min. We're going to use that repeatedly. The minimum object distance at which the eye can form a clear image, and we'll use 25 as the standard for that. The other end of the spectrum is the far point, the farthest object distance at which your eye can form a clear image, and you might be surprised that that is supposed to be infinity. Well, it sounds sillier than it actually is. Can you see stars? They're pretty far away. Can you see the moon? It is pretty far away. Like, it might as well be infinity. Okay? Do you have a question? You sure? You're positive? Okay, fine. I feel like you're going to change your mind, but I don't know. All right? So you're supposed to be able to see things far away. I can tell you this. Even with my vision correction as it is, like, I look at the stars at night, and I can see them, but they're a little blurry, right? I can see it infinity, but it's not really a perfectly clear image. Maybe some of you look up at night and you're just like struck with awe because it looks so perfect, and there's like little pricks of light, and everything is wonderful. Anybody? You want to brag? Do you want to brag? I didn't think so, okay? I can tell you this also, if I take out my contact lenses, it's more just like, there's nothing. Like, is the moon out? I don't know. Who in the world knows? I have no idea. So much, much, much less than infinity. We're going to call this D max, the farthest object distance at which an eye can form a clear image. So we're going to use this as the standard numbers for the eye, and we're going to look a little bit at, I can't write all of a sudden, standard, there we go, at common vision issues and how we correct them with a lens, and actually what the lens system is doing to help us out. So first of all, myopia or nearsightedness. By nearsighted, we simply mean that you are sighted in such a way that you can see near things. So things up close, happy and good. So that means we could say that your D min is either equal to or less than 25, not millimeters, but centimeters. Your D min is good. Near point is fine. You can see things close up. So even without vision correction, maybe you can hold something right here and read it just fine. So you take your glasses off at night, you're good. All right? The problem is with D max, which is less than infinity, or maybe it's, more like this. It could be much, much less than infinity. If it's anything less than infinity, perhaps you need at least a slight vision correction. And you can see this represented up above with the eye that doesn't have a lens on the top left. Notice we have a far point that is at a finite location. I can't put a far point at infinity in a diagram. It's at some fixed distance away from the eye that's less than infinity. Anything inside that far point is good. If the object is in there, it's able to form a focused image on the retina. But if it's outside of that far point, everything is fuzzy, blurry, or invisible, depending on how bad your eyes are. So what we need to do is use the eye's system that's there already. I can't see any farther than whatever my far point is, which means that lens has to create an image at that far point. It's not like fixing things at infinity. Instead, it's just working within the limitations of your eye. So if we were to write that down, we could say that we take a lens, whoops, can't write with a pointer, that takes an object at infinity, or just far away, and creates an image at D max. It's a lens that takes an object at infinity and creates an image at D max. You can see this represented in the figure, but I should point out that this is a diverging lens, which might sound surprising because we think of lenses as helping us focus on things, but diverging lenses take the light and spread it out. That sounds a little counterproductive, but take a look at what's happening in the first diagram. Notice where the light is focusing, just somewhere in the body of the eye, in the eye jelly, I guess. It has an official name. What's the official name? Oh, see, you do know things about the eye. What is it? Vitreous humor? You're sure? I don't know. Was that back on the first slide? Maybe we should test you. Vitreous humor. Good job. Let's just call it eye jelly. That's more fun. Why not? Ugh. No one wants that kind of jelly on bread. Or. Now take it all back. So the image is formed. It's still there, but the light rays are going to diverge again before they get to the retina, which means I need the image to focus farther back. It's focusing too soon. The way we can fix that is by sort of pre-diverging the light a little bit so that it focuses back here on the retina instead of this earlier location. Okay? So a diverging lens helps with myopia or nearsightedness. Question? Yeah. We'll get there. We're going to do an example in about 4 slides, and I think you'll see where that comes from. Okay? Yes? Is the problem with the eye the inability of the muscles to contract? I think you're asking a non-doctor here. Well, I'm a doctor, but not the useful kind. I think it's a different eye disease, but I'm not 100% sure. I think it's more about the shape of the eye. Can anybody correct? Yes. So you are the resident ophthalmologist or optometrist. No. I think it's more about like the eye here is a little bit elongated in the X direction, which is making the light focus at the wrong place. Okay? I'm sure that causes a problem as well, that not being able to focus the lens. Maybe. I don't know. Maybe we should ask the resident ophthalmologist again. No? Does the eye shape change with age? Anybody? Yes? I assume it must. Yeah. It stretches? Yeah. That's kind of disturbing. Huh. So it just stretches pretty much for everybody in the horizontal direction, I guess, because it seems like people's eyes sort of go toward myopic with age, but I don't know. We're talking about things I know nothing about, clearly, so let's just move on. Why not? Let's talk about hyperopia. Hyperopia, the opposite, farsightedness. You can see faraway objects clearly. So this is going to be sort of the opposite from before. So D max is good. We could say D max is equal to infinity. The problem is D min. D min is something greater than 25 centimeters. And now we're actually seeing clearly that the eyeball is a different shape here from the previous slide. It's answering our questions for us. It's just hidden in the slides. See that one? Smushed. Smushed eyeball, stretched eyeball. Smushed eyeball, stretched eyeball. Okay, so in the case of the smushed eyeball, notice where the image is being formed. It's back behind the eye somewhere. So this clearly means we're going to need the opposite type of lens. So you can see a converging lens in this case, which will help pre-converge the light rays so that it focuses sooner before it goes past the back of the eye. So let's write that down here somewhere. We'll say use a converging lens that takes an object. Looks like I'm about to write abject. Yeah, see, that's fixed. Ooh, there, that's better. An object that's too far, and creates an image at the actual near point. At or near the near point is fine. Notice in both of these, it's creating virtual images. You're looking through the lens to see what's there. So it's like we talked about on Wednesday. It's like if you wear some sort of lens correction, all you're seeing all the time is virtual images. So it's your choice. You can see the blurry real world, or you can look at the non-blurry fake world, I guess. Yeah. It should be too close. Thank you. There we go. Object that's too close and creates an image farther away at the eye's actual near point. So let's do a problem, and I'll go ahead and tell you that this is not a hard problem, but boy, it has a lot of words. Why? Whoever wrote this problem, and I think I know who did it. He was someone who taught at another university I taught at 5-6 years ago, and apparently he just had a lot to say. I don't know why. I feel like we should read this like a story and see where it goes. A friend of yours always sits in the very front row of a classroom. Yeah, all you people. Oh, we're all pointing at him, huh? All right. You like sitting closer to the back. You tried talking your friend into moving back a bit, but he absolutely refuses. Yes, he absolutely refuses. Okay, good. While sitting outside with your friend a few weeks ago, you pointed to a bird in a tree somewhat nearby and asked your friend what kind of bird it was. Did this happen as well? No? Forget it. This is too much. Let's just get rid of all this because that whole paragraph is absolutely pointless. We could read it if we wanted to. The idea is your friend can't see the bird or refuses to answer your question, and you start to wonder why. So this sentence happens where apparently you start experimenting on your friend. Notice, you then start pointing to some objects to find out what he could see clearly. That sounds like experiments on your friend. After this, you determine that he could see up to a distance of about 3 meters rather clearly, but things started getting a bit fuzzy beyond that point. So if we're trying to ask about near points and far points, it's just experimentation. You go to the eye doctor and they test, like, well, how far away can you read that stack or pyramid of letters that are there, and actually just physically measure what your near and far point is to figure out what type of lens is needed. We're going to use this bit of information to prescribe a lens for your friend. By the way, don't do this. Don't experiment on your friends and then tell them, like, hey, look, I ordered some glasses. You need this. Wear the glasses. So what can we determine about Dmax and Dmin for this person? Somebody help. You're all too busy writing Dmax and Dmin. Dmax is 3. I like that. 3 meters for Dmax. And what about Dmin? I like that. Seems to be essentially standard. Less than or equal to 25 centimeters. Thank you both. So what else can we determine from this? What we want to happen is for this to be infinity. We'd like Dmax to be infinity. However, we're limited by the 3 meter far point, okay? So this is where we're going to have to put the image. And we're going to use our equation from before, 1 over f equals 1 over di plus 1 over do. The thin lens equation or the mirror equation, it's all the same. And we're going to use it to sort of project what focal length lens we need based on object and image distance. So in other words, we want to be able to put an object at infinity. So we're going to put that in for the object distance. And we want things that are at infinity to create an image at that location. Okay? And keep in mind it has to be a virtual image. So let's plug these things in. We're going to say 1 over f is equal to 1 over 3, but if it's a virtual image, remember that image distance is negative, so I need to put in a negative 3 there. Let's put a little note there. It's a virtual image plus 1 over infinity. What's 1 over infinity? That's essentially 0. And boy, we've got an easy equation to solve now, right? What's f? It looks a whole lot like negative 3, right? If we want the two sides of the equation to be the same. Yeah, I don't think about things too much. So we can say that the focal length of my lens needs to be negative 3 meters. And check out that negative on f. This is the curly version of f. I should try to keep that similar to what we had before. The negative there gives us information. It tells us what type of lens, whether it's converging or diverging. So what type of lens are we getting? You're like, I don't remember. That was Wednesday. And everything from Wednesday and Monday of this week, since it's not on the exam next week, it just kind of floats over you, right? And just seeps out. The other, I get it. I understand. It's diverging. Oh, you got notes. That's good. So that tells us it's a diverging lens. So if you were the optometrist, you could do these experiments and figure out where you need to create the image. And then, well, the person is nearsighted. They can see inside of 3 meters, but not farther away. You know that you're going to need a diverging lens, and the equation gives you that. But maybe things aren't rated by focal length when you go to, like, pick out a lens for this person. There is one other thing that we're using this equation to teach you about, and it is known as the refractive power. And we're just going to call this, let's just call it D. I don't know why. It's because my notes here say D, but I don't know why they say D. Let's just go with D, is 1 over f, and f has to be in meters. Where is that curly f? That is curly f. See, I told you I was going to mess up regular lowercase f and curly f. There's no way to keep this straight. So D is going to be 1 over negative 3, so that's negative 0.33, and this unit is known as diopters. Diopters, or DP. That's the number you see on your lenses. If you have glasses, or maybe you order contact lenses and it has a number on there that's a negative something or a positive something. If it's negative, you're nearsighted. If it's positive, you're farsighted. And you're probably realizing this person doesn't have it too bad, right? I don't even know if you can get a lens at 0.33 diopters. Probably a half you can. No, maybe a half is where it starts. 0.25. You can do 0.25. You have 0.25? No, but you know somebody, or you've seen it in the order form or something. Let's have a contest. Anyone greater than 3? What do you mean? Like you don't have to raise your hand. This is not like some official poll. I'm not allowed to have medical information. But if you want to be like, yay, for the 3s. Greater than 4, 5, 6, 7, 8. Okay, I lost all of you. 9.5. Ha ha ha. Told you I was blind. And also, why am I celebrating that I won that contest? That's just odd. One of the eyes is 8.5, the other is 9.5. So lenses are necessary. If they fall out during class, you'll have to help me to my car. All will be lost. Yeah. What is legally blind? I really have no idea, but I'm not driving a car without lenses. I can tell you that. It might as well be legally blind. Yes. DI is 3 meters because I need to be able to see the image clearly. And if it's any farther away than 3 meters, you're not even going to be able to see the image. I need to have it at the farthest possible distance I can see for me to be able to clearly see anything in these lenses. DO is what we want. DI is what we're going to get. So maybe we could put that up here. This is desired, and this is our limitation. Okay? Anybody else? That first paragraph was totally useless, right? Your question. It's virtual because the only way we see it is through the lens. Like, we don't, stand back. That would be a terrible pair of glasses, right? You, hold a lens up, and then you hold a piece of paper, and then you look at the piece of paper to see the real image. That would be awful. So, we look through the lenses to see the image, and that's virtual. Also, if you use a negative for DI, negative on that means virtual as well. Anyone else about any part of this problem? No? I didn't think so. That wasn't too bad. That's about as hard as the math is going to get in this chapter. I hope you can handle it. Yeah, you'll be all right. Hey, look, a blank slide. We don't need that. We'll just write hi. Why not? That'll surprise the people who are looking at this later. And, actually, they don't deserve a smiley face. They're not here. There we go. This one I actually don't want to do, so we're going to get rid of that. Hey, this is fun. Let's just cross off all the slides. No, we're going to do this one. Yes. It's diverging because we have a negative number for the focal length. Negative on the focal length indicates diverging. Okay? If there's any questions about the signs, go back and look at our thin lens stuff. We have that one slide that has all the quantitative things, and it tells us what the different signs mean for different quantities when dealing with lenses. So let's finish up by talking about a few different other instruments. We dealt with the eye, just other common things that use lenses to help us see things that perhaps normally we can't. First of all, the simple magnifying glass, which, I don't know, I feel like the magnifying glass, you're thinking like, ooh, a lens, it makes things bigger in some way. Surprisingly, that's not really what it's doing. Here's the thing with the magnifying glass, and we're going to go through these 2 slides and sort of in order, a series of 4 things to explain what's happening with the magnifying glass. So when I look at something, how big I see it is all based on this angle. Okay? That's the angle that defines the size of the image on the retina. The size I see everything is based on that angle. So we'll say bigger theta gives me a bigger image. So if we look at the geometry of this particular problem, we could say that the tangent of theta is equal to what? Notice there's also theta there on the outside of the eye. Same angle. What's the tangent of that angle? There we go. Looks a whole lot like HO over DO. So the height of the object over the object distance away from the eye. We can simplify this a little bit, and we can say that if theta is relatively small, and inevitably when I say if it's small, this thing happens, and then someone asks, well, how small is small? The answer is small enough such that this is true. So you could punch some numbers in your calculator and be like, oh, I put that angle in and the relationship no longer holds, therefore that was too big. I can't tell you exactly how small is too small, but we can say this. If theta is small, then theta is approximately equal to HO over DO. If you want to just try it, put some numbers in your calculator, start with, a degree and 2 degrees and 3 degrees and 4 degrees and just divide the two things, you will find that theta is approximately just equal to the division of those two quantities. And the same as tangent theta, at least roughly speaking, as long as the angle's not too big. This is an okay approximation because if you think about it, that angle's never really that big, right? If I look at this chair and I think about, what is the angle from the top to the bottom of that chair at this distance? Well, it's not a very big angle. That's already quite small, even though the chair has some decent size. If it gets closer, the angle is going to get larger. And if I look at anything farther away, like if we stand out underneath, how do you say it? I call it the tower. The campanile? Campanile? Oh, that's just extra fancy. Campanile. Yes, I got it right? No, that's still wrong? Campanile? I'm terrible. If we stand out there, you can see the Golden Gate Bridge, right? So you look off in the distance. How big is theta in that case? The height of the object over that distance? The angle's tiny. So typically theta is going to be small, so this approximation works. So the way I can see something larger is by increasing theta. How do we increase theta except by getting closer to it, right? If I want the chair to appear bigger to me, I get closer. I'm like, ooh, look, bigger chair. That's basically how things work as far as object and image size. So you can see in part B here, they said the exact same object, just moved closer, gives me a bigger image on the retina, which I perceive as being larger because, well, now theta prime, the new angle, is bigger than theta. So we could say if the object moves closer, we get a bigger image. Can't write because theta prime bigger than theta. There's clearly a limitation to this, right? Let's say that, I don't know, right now on this tabletop, there are probably bacteria of some type. I kind of hate to think about that, but it's probably true. And everywhere else at the same time, I'm going to stop talking now and just leave. So there's probably bacteria right here. Maybe I'd like to see them. Maybe I'm curious about them. Maybe I'd like to learn about them. Well, so I look at this slide and I'm like, well, if I want to be able to see the tiny little thing and get a bigger image, I just need to get closer. Right? I mean, at some point, it's just like I can't get close enough to make the image large enough, right? We have to put something else in the way to try to help us get closer. So what you might say is that we are limited by our near point. Okay, so maybe it's not bacteria. Maybe it's just, I don't know, what's around here somewhere that I want to see that's relatively small, but it's not really big enough to see. Maybe I'm just like the word igloo on this water bottle, right? If my near point is 25 centimeters, but maybe I want to examine like exactly the shape of the L, this is as close as I can get. If I get any closer, it's just going to get blurry. It's not going to get larger to help me see it, okay? So what we need to do is essentially do something to allow ourselves to move objects closer than our near point. So you'll notice here above, they use N for near point for some reason. This is actually Dmin. This is the point at which the object can get no closer. There's nothing I can do at this point to see the object bigger and get a bigger image because I can't move it any closer to my eye. So our limitation on theta, you might say, is approximately equal to HO over Dmin. However, if we put a lens with focal length less than Dmin in the way, and the object at or near the focal point, we can get a bigger image. If we use a lens that has a focal length less than our near point, less than that near distance, we can put the object near this new point and actually still see it clearly. So what's happening with the new geometry? At this point, we could say now that theta prime, this new angle that's going to define how big the image is now approximately equal to HO over F, the focal point of the lens. And we know that F is less than Dmin, so that means theta prime is going to be greater than theta. Okay? We're allowing ourselves to move closer to than our near point, which allows us to see things closer than we would otherwise, which means now we're seeing objects bigger than we would have otherwise, which kind of makes the whole magnifying glass thing just sound less magical than maybe it appeared to us when we were 5. It's just allowing us to see things closer up than we could before. Okay? Magnifying glass. Questions, thoughts, comments? Anybody, anything? Yes. I'm sorry, what's that again? Oh, image at infinity. Good question. I actually did want to bring that up a little bit. We're going to talk about this a little bit more, but having an image that's quite far away, or at least appears far away to us, allows our eyes to be relaxed. So the magnifying glass actually has a side effect benefit of allowing us to get close to objects and see them larger, but not in a straining sort of way because it's pushing an image farther away. So I'm getting roughly parallel light rays that are reaching my eye, and I don't have to strain to see the object, or the image rather. Okay, good question. That's the magnifying glass. As we go through these last 3 slides, we're basically not going to do any math at all. Okay, I just want you to get a basic understanding of kind of how these things work, even though maybe you've studied them a little bit before, but perhaps not in the context of the information that we've had in this chapter and the last. So first of all, the compound microscope. By a compound microscope, the word compound there is talking about multiple lenses. So you can think of all this as multiple lens systems. And you can see that one lens sits close to the eye. That's where you're supposed to look in the microscope. Hopefully most of us are aware of that. You don't try to turn it upside down and look at things. That'd be weird. The eyepiece sits near the eye. You're supposed to look there. The objective sits near the thing that you'd like magnified so that you can see it a little bit better. 2 lenses. If we look over on the right, you can see how this lens system works. And I don't think I'm going to write anything here. Just get the concept of what's happening. So the object to be viewed is going to be sitting relatively close to the objective. That means it's going to be relatively close to the focal point of the objective. Okay? And now look at the 3 rays if you trace them through. The P ray, the M ray, and the F ray. They're going to go through and focus at some point on the other side. This is a converging lens, and it's going to create a real image at that point. We're just not going to directly ever see that real image because we're going to let the light rays go through that point and then begin to diverge again. If you were to take a little piece of paper and put it at this point between the eyepiece and the objective, there would be a little image on the paper, a real image that you could see. It's just at this point it would be somewhat magnified, but not maybe terribly helpful to you. Plus, again, do you really want to look at it that way, right? You're like, oh, look at the little thing on the little piece of paper. That's not a convenient way to look at it. So instead, we let the light rays pass through another lens, the eyepiece, and you can see how it, once again, obeys the rules of how we use our 3 rays. This one started parallel and goes through the focal point on the other side. And I think they've actually added a ray here that's a little bit different. Actually, a couple of these are a little different. We could draw one of the other rays we know about. The midpoint ray would go right here and go essentially parallel to the other 3 that they've drawn. But no matter what I do with the rays, they're going to essentially be traveling parallel to where I'm looking at this point. Which means we get, again, an image that's formed by the eyepiece roughly at infinity. And you get a magnification that's using the magnification of the 2 lenses. If you multiplied their 2 magnifications using the magnification equation we had from Wednesday, you get a multiplicative factor of magnification from the 2 lenses themselves. Now, I've looked through plenty of microscopes. When I was in grad school, a lot of the work we had to do was with circuits, like at a really small level, and we had to do little things under a microscope. And I always found it a little bit hard. I don't know about you, but my eye doesn't feel terribly relaxed when looking through a microscope. Anybody else? Like, it feels like you got to get your head, especially if it's a stereo microscope, and you've got to kind of get things just in the right fashion, and then maybe things are okay. If the light rays are roughly parallel, it's supposed to be relaxing for your eye muscles. I guess that part's true, but it still can be a little bit of a fight to see things clearly and not have to work at it a little bit. Remember Wednesday we talked about virtual objects? Like barely? That's what's happening here. This image that's being formed by the objective is the virtual object of the second lens. It's not an actual object that's there. So we could say that this is a virtual object. Nothing is really there, but it's the thing that the eyepiece is magnifying. 8 minutes remaining. We are going to finish this chapter. fantastic. Compound microscope is almost exactly the same as the refracting telescope. For the telescope, we're just trying to look at things that are far away and magnify them. So the real difference is that instead of this object sitting close to the objective and its focal length, the object is very, very far away from the objective. Other than that, you can trace these rays through and see that the exact same thing is happening. You have one lens that the light enters from the object, and then the eyepiece is near your eye. All the ray diagram and everything works exactly the same. So it's really no different than what you saw on the previous slide. That's all I want to say about that. The problem with this slide is that it's limited. Think about these pieces of glass required to build a telescope. It turns out that the bigger the lenses are, the more light can enter the telescope itself. So people start building telescopes to see fainter and fainter and fainter objects out in the cosmos, and they're like, ooh, let's just make a bigger telescope. So they make a bigger lens, and they're like, well, we still didn't see what we wanted to. Let's make a bigger lens. And they make a bigger lens. And at some point, you run into the problem of all that glass. You don't want to use plastic because it's just not clear enough and perfect enough. It gets heavy, right? You can imagine you get a lens that's so big that now the lens itself bends under its own weight. That's not a very helpful lens anymore. You've got a bit of a problem. So this type of telescope is size limited because of the way it's built. You can only use it for certain circumstances, and if you want to see something that's really faint and really distant, you need a reflecting telescope. In this particular case, we use a mirror that takes the place of the objective lens. So this replaces the objective lens. And it bounces to another mirror, and then there's an eyepiece once again. You don't need to know the details of what's happening here. I just want to point out that this primary mirror is not size limited based on the same things we talked about as far as just bending. If it's a mirror, you can build a reflecting surface and put a big support under it. Notice, look at that beautiful support. See? Look, it's gray and it looks strong, like it's concrete or something. Also, look, it can float. Ooh. Fancy. No, none of that's happening. You get the idea. I could build this like into the ground and make a big, huge sort of concave surface and make the whole thing reflected, and I can keep making that bigger and bigger and bigger just based on construction limitations. So this allows us to overcome the benefits that we had for the refracting telescope and instead see objects that are even farther away. That's optical instruments, okay? Just to close things out, I need to point out some limitations. Limitations of these, we'll be done with the chapter, we'll be done with the week, and we have an exam next week, and I think only 4 weeks of class remaining. And then we're just going to want to start up and do it again, right? 8A, we don't want to leave each other. No, yeah, let's just do 8A again next semester and 8B, and we'll just continue this back and forth. It'll be fantastic. All of us will be gray and old, but boy, we will know introductory physics. We will be some smart people. So a couple of issues with lenses that you may sometimes see that I just want you to be aware of. Spherical lenses, just like spherical mirrors, have some issues with blurriness. How do you like the way that light is focusing? Wow, that is beautiful, don't you think? A spherical surface, if the rays hitting the sphere are too far away from the principal axis, you're going to end up with focal points that are different for different light rays. So you want to sort of restrict this a little bit so that the light that hits the lens is closer to the principal axis to get everything hitting the same focal point. This is known as spherical aberration. And, well, you've either got to shape the lens a little bit differently or you have to restrict the light that's incoming to make sure that you get light focusing at the right point. The only other lens issue that I should tell you about is chromatic aberration. Chromatic, you should be thinking about color. And one thing that we didn't discuss is that just regular old glass has different index of refraction for different wavelengths of light. When we dealt with this so far, we just said, piece of glass, just light that's a mixture of all wavelengths, has this index of refraction. That's a good approximation. However, if you need a very, very accurate image and you don't want any imperfections in the image that you're seeing, You might have to consider that just white light is a mixture of all the wavelengths of light, and as it enters a lens, since it has a different index of refraction for different wavelengths, different colors of light are going to bend a slightly different amount, which can result in a splitting of colors. I don't know if you've ever seen an image where, like, kind of around the outside, there's like a rainbow effect in the image. That's what's happening. Different refraction amounts for different wavelengths of light. So you can see here it says that a lens bends blue light more than red light. The general rule is that the index of refraction goes down as the wavelength goes up. Higher wavelengths have a lower index of refraction for a piece of glass. So you can see they separate. So the result that you want to get is to bring all that light back together, and I can use two lenses. A diverging lens that's going to bend the light one way too much, and then a converging lens that's going to bend the light too much another way and sort of cancel out that effect and get all of the light to come together at the same point. So maybe if you have a really, really fancy camera, maybe you're the type that wants to take like really beautiful photos that are perfect, and maybe you're an artist instead of just a photographer, and maybe your camera costs $5,000. You probably have lenses that were really, really, really expensive, and they build in multiple lenses to correct for chromatic aberration, something that you're probably not going to get from your smartphone camera, but maybe you don't really care about chromatic aberration so much in that case. Yeah. Why do they have different refractive indexes? That's because we ignored some of that a little bit too. So I'm pointing out some of the issues that we often just overlook. But that's all I can say about that for now. Anybody else? Are we done? That's it? No, we got one more question. Don't go anywhere. Yes? Yeah, that's just the name of putting two lenses together in that form to correct chromatic aberration. Okay?